Our last method for solving systems of equations is called Cramer's rule. And it has one thing about it that's really attractive, that makes it seem like a really good technique, and that is, it's very easy to state Cramer's rule and to memorize Cramer's rule. With Cramer's rule, you basically make a grid out of the coefficients of your variables, just the a's and the b's, the coefficients of the variables, and that makes your denominator. And then for your numerator, if you're solving for x, you replace the x column with the constants. And if you're solving for y, you replace the y column with the constants. And that exact same procedure for making the answers to a system of equations, that also works for 3x3 systems. And honestly, if we went that far, it would work for 4x4s, it would work for 5x5s, and any size system of equations. You could do them all the exact same way. You would take the coefficients of the variables and build your denominators. And then for each variable you're solving for, x, y, z, whatever, for however many variables you may have, whichever variable you're solving for, you replace that column with the constants. So if I were to ask you to sort of like draw a picture for what Cramer's rule looks like for 4 equations with 4 variables, you could probably do it already. It's a very easy system to memorize, and so that's a big advantage. The other big advantage with Cramer's rule is that in a lot of systems of equations, you don't actually need to know the answers for all of the variables. Maybe you just need to know what x is. Maybe you just need to know what y is. And with Cramer's rule can let you solve for one variable by itself and ignore the other ones. And you don't have to do anything with the other ones at all. So the advantage to Cramer's rule is pretty obvious. Easy to memorize, lets you solve for one variable at a time. What's the problem? Well, the problem is, what are those grids? That's a pretty natural question that you should be asking. So if you want to know what the grids are, the first thing that you might think is you might think from the lecture that we did from section 8.6, maybe they're matrices. Well, no, they're not matrices. What they are is they're a type of thing called a determinant. Determinant. These are determinants. And yes, they do look a lot like matrices, but they're actually really different from matrices. For example, when you work with matrices, you simplify them, and when you're all done, they're still matrices. They don't change their nature as you work with them. But with determinants, each determinant you have, each grid of numbers, whether they're grids of 9 numbers like you have there, or grids of 4 numbers like you have up here, or even larger 4x4 grids or 5x5 grids, the grids are always square, and you're always computing them down to a number. They always compute down to be a number. Like here, this grid in the bottom is a number, this grid in the top is a number, and you end up with x is a fraction with a numerator over a denominator. So the real challenge with Cramer's rule, the downside, the hard part, is you have to learn how to evaluate these determinants and get the numbers out of them. So we'll start with the easy stuff. We'll talk about how to evaluate a 2x2 determinant, and then we'll talk about how to do the more complicated kinds of determinants. Luckily, the rule for working with determinants, at least the 2x2s, is very simple. You work out 2 different products. So one product is where you go in a downward diagonal fashion, and you multiply those 2 numbers together. And then there's another product where you go in an upward diagonal fashion, and you multiply those 2 numbers together. And the value of the determinant is those 2 products subtracted. It would be better if it was added, I know, but subtracted is what it takes to make a system of equations actually work out properly. So if we're doing this individual determinant here, the downward diagonal, 8 times 2, would give us 16. The upward diagonal, 4 times 3, would give us 12. And when you go 16 minus 12, your final answer result would be 4. So that's an example of working out a 2x2 determinant. and you'll probably get very good at them very quickly. And if you're using Cramer's rule to do two equations with two variables, you'll probably find that it works pretty well. It's pretty fast. It doesn't really require you to do a lot of planning ahead or thinking through steps. You just crank out the numbers and it gives you the answer. So let's move on to talking about bigger determinants for doing larger systems of equations. This is unfortunately pretty complicated. The technique I'm going to be teaching you here is called expansion. And I'd like to warn you, there are shortcuts, and if you go to like a tutor or come into my office hours or something, I can show you some shortcuts, and I'm sure the tutors will show you some shortcuts. But the shortcuts are always special purpose. They apply to a particular type of thing. What I'm going to teach you with expansion is something that would work on any problem. So the first step of expansion is you pick a row or a column of your matrix, of your determinant. So you pick any row or column. And as you get more practice and you're able to sort of see where you're going with a particular problem and what the advantages and disadvantages are, you'll eventually start realizing some rows are better than other rows. Some columns are a better choice. But for right now, just imagine for some reason you picked a random one of some kind. So this is just an example. You don't always have to pick the second row. I'm just saying, what if you picked the second row? So then, the value of the determinant you're going to get out of this is you're going to start with each of those numbers. So you're going to have A21, A22, A23, and so on, because there might be a bunch, who knows. And for each one of them, you multiply by a thing that's called a cofactor. So there's going to be a cofactor that goes with A21. There's going to be a cofactor that goes with A22. There will be a cofactor that goes with A23. And once you figure all that out, you add up the results. Okay, well, that obviously just pushes the problem back one. Now the question is, what the heck are the cofactors? Each cofactor is going to be a combination of two things. It's going to have either a plus or minus sign in the front multiplied by a smaller determinant. So, like if we're doing a 3 by 3, you're going to be breaking it down and each cofactor will have 2 by 2 determinants in it. If for some reason you were doing a 4 by 4 determinant, it would break up into 3 by 3s. So there's a sign in the front, a plus minus, and then there's a smaller determinant. The plus minus business has a fairly simple rule. It starts with positive in the top left corner, and then it's just sort of like a checkerboard. You go through all the rest of the entries, and it's either positive or positive or negative, just alternating like a checkerboard. So, for example, that A21 that we started with in that row, that would have been in a negative position. So that would have been a minus sign for the cofactor. And then the smaller determinant, they're called minors. So, for example, if you're trying to figure out the minor that goes with A21, you've got negative, because it's in that second position. And then to figure out the minor that goes with A21, what you do is you eliminate that entire column and you eliminate that entire row from the determinant, and you keep whatever's left. Okay, that doesn't make a lot of sense. Let me show you an example. If I show you a picture of what I'm talking about, it might make a little bit more sense. So, actually, let me get rid of these for a second. I'll bring them back in a moment. Let's say we're trying to work out this 3 by 3 determinant, and we're going to do it by expansion. And let's say, at random, we pick this row here. According to our rule, the answer here is going to be 1 times some kind of cofactor, so something's going to go in here, plus 4 times some kind of cofactor, something's going to go in there, plus 0 times some kind of cofactor, and something's going to go in there. And you can already see that because of the way this works, zeros are kind of nice. If you get a 0, you don't have to worry about the cofactor. The whole thing equals 0. So I can totally skip the third term, don't have to work out any other details for it. I only have to worry about the first two. So then the question becomes, okay, what are those cofactors? I'm getting 1 times what and 4 times what? Okay, well, first of all, there's the plus-minus pattern. The 3 is in a positive location, the 1 is in a negative location, and the 4 is in a positive location. So I've got a negative sign here, a positive sign here, and then the actual cofactors. So to figure out what the cofactors are, let me copy this picture and realize since we're doing the cofactor that goes with 1, we cross out that row, we cross out that column, and look at what's left. We're left with -9, 4, -3, 1. Let's do that again over here with the second one. Let me bring down the determinant here and realize for this one, since we're doing the cofactor for 4, we cross out its row and its column, and what we're left with is 3, 4, 8, 1. So, let's clear up all the distractions there. We've got 1, we've got negative, I guess -1, and the determinant -9, 4, -3, 1. And for this one we have 4, and it's positive, so +4, and the determinant 3, 4, 8, 1. So the question now is, work out those two determinants, fill in those results, and you'll finally be able to compute your answer. So let's see, 2 by 2s. Got to think back, how did we do 2 by 2s? There's a downward diagonal. -9 times 1 is -9. There's an upward diagonal. -3 times 4 is -12. And we subtract them. So that's going to be -9 plus 12 is going to be 3. For the second one over here, the downward diagonal, 3 times 1 is 3. The upward diagonal, 8 times 4 is 32. You subtract them, that makes, let's see, what is that? -29. So we've got -3 and -4 times, positive 4 times -29, which is 116. So we end up with a total overall value of -119 there. Now you can see, doing a 3 by 3 determinant, it's a lot harder than doing a 2 by 2. Let's just scroll back up and compare them. 2 by 2 determinant was just a matter of seconds. One little multiplication, a second little multiplication, some subtraction. 2 by 2's, piece of cake. Very simple. But for a 3 by 3, I had to break it up into 3, well, I got lucky this time, 2 individual 2 by 2's with a few extra bells and whistles, some other like the 4 and the positive or the negative sort of thing going on. So a 3 by 3 is going to usually take you about 3 times as much work as a 2 by 2. And it gets worse from there. If you were to move up to doing a 4 by 4 determinant, it would take you roughly 4 times as much work as this 3 by 3 did, which was 3 times as much work as a 2 by 2. So this is really the big problem with Cramer's rule. As your determinants get bigger, they get more time-consuming very rapidly, very, very rapidly, to where I've never really seen anybody use Cramer's rule to do a 4-equation system, except once, where the professor was just showing off. Look, I can do it. It was definitely not a practical method, and trying to do it on a 5 by 5 would just be a joke. So although Cramer's rule has some attractive principles, that it's easy to memorize, and it has this nice ability to solve for just one variable at a time, it has some massive disadvantages in terms of actually trying to get answers.